nanoengineering. Shirley has won a wide number of awards, including most recently the Electrochemical Society Tobias Award, before that the NSF Career Award, the UCSD Chancellor's Award, and a wide number of others that I will not spend that much time repeating. So today she'll be speaking about her work on advanced operando characterization of battery materials. So please join me in welcoming Dr. Shirley Meng.
Thanks, Yi-Yang, for the invitation and the very nice introduction. So the last time I came to Stanford to give a talk, it was 2006, okay, when I was on the job market. I didn't get a job, but still, it was a very pleasant journey. Always happy to come back to the Stanford campus. You know, I know that Stanford has a very strong battery research, energy storage materials groups. You have several professors. So it's a very difficult talk to give because obviously the world's expert, Professor Bob Huggins, are also in the room. So, and many students who spend a lot of years working in energy storage. So let's see if you can actually, after the talk, feel like you learned something you didn't know before, okay? So some motivation behind why I spent my entire career, which is quite short, only 15 years from graduate time, on the topic of energy storage. I think it's important for us to remember that the trend right now is to try to make everything run on electricity. So to decarbonize, we need to work on transportation and electricity generation. I think the reason I put up the slides here is to show you that the public sector R&D for energy storage is in the order of tens of billions of dollars, and it fluctuates over the years. I think I myself experienced the dip here in the 2000s, almost changed my PhD topics because everyone runs for the hydrogen storage research topic. I'm glad I did not change, but I just want to let the students know the funding fluctuation is a natural cycle of the United States. And I didn't change, but you know, we also should remember that for the Apollo project, it's $1.6 trillion for bringing a man to, you know, so the order of magnitude is different. So if we consider this bring down the CO2 level, the deep decarbonization as one of the major human mankind challenges, we're way underfunded, okay? So we should have some confidence that, you know, that there will be more money on the way. Okay, so this graph you have seen many times. I think Professor Nate Lewis from Caltech used this many times to educate the public that we have a terawatt problem. I will use the graph a little bit differently to introduce two important things many of you probably already know, that low power device like light bulb, high power device like the toaster, right? For light bulb, you use 16 hours, or for the toaster, you use a few minutes. So the energy content is very similar, but you know, the magnitude order difference in the power requirement. And also in terms of the watt hour, of course, watt hour is a big unit. So a lot of people don't realize in the battery jargons, we usually talk about a few watt hour, taking out our cell phone and show that's, you know, a few watt hour or 10 watt hour. But 1 watt hour is 3,600 joules. So we need to realize that it is a big energy unit, okay? So in my research group, we work from miniature batteries for wearables, for credit cards, those thin film batteries. We use those as a vehicle to study interface, okay? We also, of course, work on intermediate size of batteries, mostly for portable electronics, or DOE found us a lot for the electric cars. So I think for e-mobility, looks like lithium-ion batteries is indeed the winner. And right now, the challenge is how far we can bring the lithium-ion batteries into the commercial world. This picture is taken from UCSD, the actual UCSD 5 megawatt hour huge batteries. It's 5 containers. So if some of you come onto the campus, you can ask me where it is located. You can take a look. 5 huge containers of lithium iron phosphate batteries. Okay, so this whole range, and I can tell you these batteries actually now is not, it's going to take us at least 30 years to recuperate the cost that we have. You know, we bought this a few years ago when the cost is still above $700 per kilowatt hour. Okay, so with this variety of range, I just want to put perspective. So our human brain is like the laptop, about that power consumption, energy consumption. Unfortunately, some of my students only work 2 hours or 3 hours a day, so the total energy content is quite limited. Okay, I think, of course, we want the students work like, you know, much more powerful, like electric cars. Okay, so now the first part of the talk, I'm going to talk about a device you all think you know everything about it. Okay, but hopefully I can show you there are things you don't know about the device. Okay, so lithium-ion batteries, 25 years old. Last year, actually, 26 years old this year, because we celebrated the quarter century birthday for the commercialization of the lithium-ion batteries. I think very importantly, you see a recent trend in the academic research institution. People start to do much more full cell studies. Okay, why? Because there's a very important limitations for a closed thermodynamic system. So all of you, you know, should read the Professor Huggins' book on the battery materials. Okay, closed system thermodynamics, energy can go in and out, not matters. Matters cannot go in and out in the closed system. So when you have a closed system, you have limited amount of lithium. Okay, in full cell, you have limited amount of lithium. The system tolerance for any inefficiency, it doesn't matter it's SEI, it's, you know, the battery material itself is falling apart. Anything has inefficiency and consume lithium in the irreversible manner, your decay is amazing. And this is not rocket science. We just do a spreadsheet with Excel, and you see that today's batteries run on 3.9 efficiency, 999. If you do 99 without the third 9, after 300 cycles, your batteries cannot function anymore. Okay? I know a lot of students don't believe it. Once you start doing full cell, you're going to see the effect very clearly. Okay? Because most of the academic institutions or research groups in the previous, you know, last 2 decades, we do a lot of half cell with huge, we don't use, you know, graphite or silicon with no lithium in it. We use lithium metal for the half cell. Then you have excess amount of lithium, and this effect does not show up. Okay? And for now, I think a lot of students are working on lithium sulfur system. Sulfur system, the efficiency is only 98%. So you will have to put in 2 to 3 times of excess lithium in order for your cell to cycle a few hundred cycles. Now, for electric cars, we all have to go to 3,000 cycles. So what's the way to go above 99.9? Okay? Now, then we translate this to think about, I'm a material scientist, okay? The first thing is to figure out where is the 0.1% efficiency loss? What kind of scientific instrument allow me to measure the 0.1% inefficiency loss accurately? I think that's very challenging, as I will show you later, because in the you know, for instance, conversion materials like lithium sulfur, lithium oxygen system, we don't even reach that point yet to talk about the 3,000 cycles. How do you measure and quantify the 0.1% inefficiency? I put this one here because I used to talk a lot to the electrical engineering and the mechanical engineering colleagues. They always think the battery is just a black box that you take electron out and you stuff electrons in. But I think for this audience, you all know that batteries is much more beautiful than a black box, right? And over last decade, I think the field of batteries clearly, we spend a lot of time to educate people who are not in the battery field that in actual lithium-ion batteries, there is the ions. You get electrons from the mobility of ions. And there is a bond breaking and the formation in both electrode materials, right? And that's the fundamental difference between batteries and supercapacitors. The dynamic phenomena, because the lithium is a matter, the matter moves, then the volume is going to change, okay? So oftentimes, we consider the batteries go through 1,000 cycles, just like airplanes served for years of service, taking off and landing. The fatigue due to the pressure differences is very similar as when you cycle the batteries. It's the electrochemical fatigue process because the volume change, even if it's only a few %, because we're using oxide materials, they are ceramic materials, a few % is very significant. And then until now, the battery field still have not break this curse of half-half rules because when you do materials to the cell level, you lost half of the density. When you go to the cell to module to the pack, you lose another half of the energy density, right? So typically when we say, when you have a lot of the low energy density cells, like sodium-ion batteries, aqueous batteries, per cell has very low energy density. So all these inactive materials like the containers, the separators, you have to make it a lot. So, the weight for the inactive is typically not considered when we're calculating, comparing the different technologies. And the lithium-ion battery field today, for instance, if you look at the entire module of the cells, there's still more than 30–40% of the inactive materials that cannot participate in the actual electrochemical reactions. Okay, so over my time as an independent assistant professor, associate professor, and leading a research group in UC San Diego, I think I was very lucky because we were funded through the Energy Frontier Research Center by DOE Basic Energy Sciences. So my question is always the 0.1% inefficiency because we are trying to close the gap. There are two gaps to be closed. Number one is to ask ourselves why 3,000 cycles is so difficult to achieve in even the conventional layered oxide. Okay. The second thing is why can't you achieve the entire capacity? For example, 1 electron per transition metal. Like why can't we get there? Right? Is this really just the electrolyte problem? Because I think the electrolyte people are making a lot of progress. Very soon we will have 5-volt electrolyte. Can the layered oxide or the intercalation oxide still deliver its maximum capacity? So when I started my 10-year track, a lot of my attention was paid on the atomistic level. Okay, over the last few years, I start to spend more time on primary particle level. Okay, and today I have a very good conversation with Professor Will Shu, who's definitely working a lot on the secondary particles. What's the best morphology, porosity, and now here, the electrode level, still a big gap because right now most of our batteries on per centimeter square, there's less than 100 micrometer thick active cathode. Can you grow to 500 micrometer? Why can't you do that? What's the transport limit? And if, say, somebody claimed I can make a 500 micrometer thick electrode per centimeter square, ultra thick, do we have the scientific tool to prove that the lithiation and the delithiation is actually uniform, right? So there are a lot of research opportunities here to answer some of the fundamental questions. So the nice thing about a fund that coming from basic energy science is that the tools we developed here, it doesn't matter what is the battery materials, then we can use it for example, the lithium sulfur system, because lithium sulfur system also are looking at how to improve the loading for sulfur. Okay, so I want to quickly show a brief history of the electrochemical energy storage, because I was always asked by a lot of people when the next revolution is going to come from. So you should look at the last 200-300 years of history. I'm pretty sure the lithium-ion batteries is considered revolutionary, and ask ourselves, can I have another revolution, I guess, 25 years after the last revolution? Okay, so that's, I think, we should always aim for revolutionary change, but remember that revolutionary change, paradigm shift, does not come so easily, so frequent. Okay, if you look, so I simplify this graph in a very, so my colleague Ping Liu, we used to work in APA-E, now is a faculty in UC San Diego, put this very nice figure together. The x-axis is structural change, no numbers, it's just very intuitive. The y-axis is the delta G, and all of you, if you've read Bob's book, voltage is a measure of the chemical potential difference, which is the partial derivative function of the Gibbs free energy. Okay, so humankind has been very lucky in the last 200 years. We were along this trajectory of higher free energy, okay, and less volume change. So we have higher energy density, we have longer cycle life. And over the last few years, when lithium iron phosphate was very popular for a while, we noticed a counter trend. Yes, the cycle life is longer, but the delta G is actually less. Okay, everybody wants to go here. The most desirable place is, can we go even higher in delta G and less structural change? Okay, because typically the structural change with lifetime, they are positively correlated here. Okay, less structural change, longer life. So we will have to come out with certain, out-of-box ideas. Okay, so the roadmap for the battery field, is quite clear. I think a lot of people are quoting this graph coming from the J. Caesar in the Energy Hub for the battery storage. That shows that in terms of the y-axis is the volumetric energy density, we cannot give up on the traditional intercalation materials. Okay, so this is manganese-rich NMC. It's typically called a lithium-rich layered oxide. So my first example is going to show you, is it possible to go very high volumetric energy density with lithium metal paired with this well-known for 10 years already, the oxides, okay? By weight, there's no doubt lithium oxygen and the lithium sulfur are much more superior than the traditional intercalation material, because in intercalation, the host structure does not participate actively in the electrochemistry. So lithium sulfur and the lithium oxygen, even though we are not ready, maybe not, especially for lithium oxygen, we are not ready to go commercialization yet. But as I previously been interviewed by ECS, Electrochemical Society, we are scientists, we are allowed to dream, okay? So do not always think when it's going to, be commercialized, but think about the fundamental challenges of lithium oxygen and lithium sulfur. The other important roadmaps that we often use for the grid storage is, again, coming from the agency APA-E. I really like this graph because typically the power cost for the grid is not highlighted. Okay, this graph shows that the pumped hydro and compressed air are very good in terms of energy storage, dollars per kilowatt hour. They are low cost. But their power cost is exceptionally high compared to the electrochemical energy storage, right? Because, so my father actually is pump hydro specialist, okay? So the progress for pump hydro has been really great. The efficiency is very high now, okay? The new generation. And, you know, I think we should realize that with today's modern grid, with a lot of the wind and the solar, there is a component that need the storage to respond to the demand at a very fast fashion. So the power cost must come into the consideration. And when you consider that, you can see that electrochemical device has its advantage, right? And this corner, of course, is the desirable place. And I have many dots here because I believe which chemistry is going to win is still unclear, right? Lithium-ion is right now maybe ahead of some of the other technologies, but it still haven't go over this line yet, even though it's getting really close, okay? And this line is also a moving target, okay? Some venture capitalists will tell you this line should be $50. Some people tell you it's $100. But no matter what, I think in terms of the system level cost, the electrochemical energy, so there's materials level cost, cell level cost, and system level cost, still way away from here. Okay, so enough of the background. I think I will now start to give you an example about new materials that our group is been spending the last, I would say, 8 years, special focus on this particular material. So when you start a battery group, and I know I talked to quite a few of you, many of you want to become faculty members or research leaders in the energy storage. So of course, it's always good practice to put together what's your expertise, what you're good at, and then think about, 50 years ago, all the brilliant scientists like Bob and Stan and Professor Goodenough, they work on this problem. So if I come in today, of course, beside you are probably more brilliant than the other scientists, but what are the tools available that today we can use, but 50 years ago are not available, okay? So I think, let me show you, of course, computation. I remember 10 years ago when I was interviewing here, I actually talked about computation and the experiment. How do you combine it? There's this debate, I guess, whether a person can do both computation and experiment. I think the right phrase is nobody can do both theory and experiment. Okay? And I want to take this opportunity to set the record straight that computation does not equal theory. My husband is a real theorist, so I know what theorists do. They don't need computers, okay? So computational tools, like any of the advanced experimental tools, it is very, very powerful because today you can code a lot of theory into computers, and you can calculate large amount of properties, especially thermodynamics or quasi-equilibrium kinetic properties, okay? So you can integrate computation into part of your planning for the experiment and shorten or save manpower and time. But that is not equal to doing theory, okay? Doing theory is much more difficult because sometimes the paradigm shift for the theory, the way how you think about, for example, what give you the highest voltage, right? Is there a new theory says I can build a single cell that have 7 volts, right? So that's very different from computation because we use existing theorems, we code them in the computers, and it helps us to plan our experiment and shorten the time for development. So I think for this audience, I'm just telling you, I was the first experimental student in a theory group. Gersida at MIT, now in Berkeley, just your neighbors, did a lot of development work on how do you compute those properties. And I think the progress is very amazing. That's why those techniques has been widely applied in the materials project. So I'm just showing you the example where Gerd showed in his MRS award talk. Yeah, I mean, if I have an experimental student to test every property of the known compound in the ICSD database, guess how many years the student has to spend in the lab, right? But this is one of the computational results of every single known compound in the ICSD database of its voltage versus lithium and the capacity, how much, okay? People use the data. A data sit in front of you. You will use it very differently based on your expertise and background, right? When I look at this, that corner, high capacity, high voltage. Did you notice there's nothing else but oxides, right? All the other phosphates, borates, silicates, sulfates, they don't go there. Okay, so it is very clear why I spend most of my tenure time, during the tenure track time, on oxides. I only started doing sulfur after I got tenured because can take more risk now. Okay, so if you look at the comparison between the classical layered oxide, which, for example, NCA, think about the Tesla batteries, NCA, okay, and these what we call the lithium-rich layered oxide. The only thing you do is you put extra lithium in the transition metal layer, okay, and the percentage of extra is only 10 to 20%. You don't need too much of it. Okay. Reversible capacity 300 now is routinely obtainable in many people's lab. It's not just a few small labs, right? And the prototyping facility we collaborate in China, they make 1,000 kilograms of those materials, and they gave 300 milliampere per gram reversible capacities. Okay, I'll come back to the problem with these materials later. Okay, because this has been commercialized. So the first thing is, I think, if you are somebody looking for completely out-of-box ideas, it's not that exciting because how much energy density I actually increase? Maybe only 20, 30%, right? Because the voltage is actually slightly lower. But you have to think about the here, for instance, in the NCA materials for the high voltage, right? I only get less than 1 electron per transition metal. In the lithium-rich layered oxide, I can get more than 1 electrons per transition metal. So from the electrochemistry perspective, it is really exciting because in the last 10 years, we solved two problems. One is, look at the first cycle irreversible capacity. We can reduce it to less than 5%. So almost no irreversible capacity during the first cycle. Okay? And I'll show you later how you can solve the rate capability problem as well. Okay, so fundamental stuff first, computation. So remember that computation are not supposed to use to replace experiment. Okay, we should do things experimental people have very difficult time to do. For instance, if I measure the density of states of certain materials, it's very difficult to separate, deconvolute the density of states contribution coming from the transition metal d electrons or coming from the oxygen p electrons. But in computation, okay, if you believe density functional theory is correct, okay, some people don't believe DFT is correct. Some physicists have major challenges for those theory. Then we will have a separate conversation. Okay, if you believe the density functional theory can, deal with valence electrons accurately, this very simple calculation is the classical layer material. So instead of plot the transition metal in the center, I plot the oxygen in the center. So the layer below is all lithium. The layer above is all transition metal. Okay? So when you put excess lithium in it, then the layer previously occupied by the transition metal now will be occupied by lithium. Okay, it was surprising, but the oxygen band, P band, is pushed up closer to the Fermi level. And then those calculations in a different materials, like Li2MnO3, has also been calculated by Cedar in his chemistry, Nature Chemistry papers separately. So after this, let's look at some of my old experimental data. Old is in like 5 years ago, because when we did this work, we didn't realize how much information we were getting from this material. You can see this is a 0.8 Armstrong resolution STEM image, right? You can see beautiful layered structures in this material, transition metals, and then the fuzzy ball is oxygen, and then there's a very good transport for oxygen for the lithium ion. Now, after high voltage cycling, people sees that the surface, the transition metal comes to the lithium layer, so it forms some kind of defect spinel-like structures. Okay, so immediately, I think there are a lot of reproducible results from entire field. A lot of people sees those kind of surface transformation. But I want to point out here that if you made a good material, this layer should not grow inside the bulk. It's actually a surface passivation layer here. Okay, when you do the yields, you're going to find that the oxygen K edge significantly changed. So there have been a lot of people using X-ray absorption spectroscopy. So if you do a lot of spectroscopy studies, please understand that EO's resolution is typically only 1 electron volt. Right? XAS, you can have 10 times better resolutions, but STEM EOS has the local ability, right? In XAS, it's mostly averaged out. So here, the first hint, we think something happened on the oxygen. Okay, so now we use neutron scattering because, TEM people always get criticized that you only look at, you're the blind person touched the elephant, okay? So now in neutron, this is done in Vulcan beamline in Oak Ridge National Lab. Again, I think 50 years ago, 60 years ago, it's rather difficult or impossible to conduct this experiment. And now these tools are available for everybody. I think even, pouch cell, we will have found the industry like collaborators so that we can make those large scale, because for neutron, if you want to limit the experimental time, you need a larger amount of the battery materials, and you can't really use the coin cells. Okay, so I think for this audience, I don't have to repeat, but X-ray, you can't really see lithium ions, but in the neutron is probing both the electron and the nucleus, so the lithium and oxygen, nickel and manganese, the contrast can be seen much more clearly. And of course, our major interest here is the oxygen, right? So there are a lot of know-hows of how to do operando neutron experiment, mainly because neutron, proton has very high neutron signals, so you need to do something special about the neutron cell. But you can actually make a pretty good signal-to-noise ratio, and you can track how the lithium, for instance, like in the first region, second region on discharge, how the lattice change, how the lithium gets extracted and goes back. I think the most striking information we found out is that the oxygen loss is definitely happening, not surprising for many people, but we see partial oxygen coming back to the actual bulk lattice at room temperature. Okay, so we have a lot of difficulties in publishing these results because room temperature, you have oxygen mobilities going out and come back. So first of all, my own thesis advisor did not believe it. Right? I mean, of course, he's no longer my thesis advisor, so I can still publish without him agreeing with it. But there's a lot of debate in the field. Okay? So I think I want to put this out here that oxygen vacancies This part gets lost, probably explain the irreversible capacity, but we definitely seeing oxygen play a very significant role. But remember, if the oxygen goes out, we still don't know, is the oxygen lost as a gas phase, or did the oxygen get lost and form another solid phase, and then it can come back to the structure? Okay? Those experiments cannot tell us the answer. It gives us an observation, but it cannot tell me if oxygen actually, what product did the oxygen come from. However, as a ceramics trained material scientist, I do know what are the possible methods I can suppress the oxygen gas loss. Okay? So I can use an engineering approach to treat the particles of the lithium excess materials, which all have, 150 to 200 nanometer primary particles, tens of micron secondary particles, very beautiful ordered structures. I can find a gas phase treatment where I pre-create oxygen vacancies, because in the studies we did is that the partial pressure of the oxygen is 1 over the concentration of the oxygen vacancies. So if I have some oxygen vacancies, I lower the oxygen partial pressure a lot, I can suppress the gas release. Okay, the outcome is quite amazing. You can actually repeatedly get more than 300 milliampere per gram reversible capacity after you suppress the oxygen loss, and you can cycle these materials quite well. So I hope, just this example to show you that even in the materials that we have known for decades, there are still some very interesting new science, especially now I think a lot of people are doing these oxygen redox activities at room temperature in solid state. I think it's quite exciting to open up this field for people to explore. And we have to make it happen, because if you look at the NCA, even NCA can go to more than 220. Look at the comparison, okay? First generation lithium cobalt oxide, NMC, NCA, lithium-rich layered oxide. The trend is clear that, it will bring your energy density up. And then we wrote this in the perspective article in Chemistry of Materials. Can somebody make lithium oxide as energy carrier, where you can actually, go beyond 400 milliampere per gram, right? I think thermodynamically it's possible, but how can we enable it? That's up to all the brilliant new students, whether somebody can make a breakthrough. Okay, so the second example I think I want to quickly show you is this state-of-art coherent X-ray diffraction. I think, like I said, after I got tenure, I could do a little bit more risky stuff. So start to look at things at primary particle, okay? Primary particles, traditional X-ray, a lot of people get used to it, right? You do the X-ray, multiple particles start to diffract, you get information about how the phase change. Now, if you focus X-ray, X-ray, we can focus X-ray to a single particle that fulfill the Bragg diffraction conditions, okay? So no lens, okay? You just have the wave comes in, interact with the lattices, that wave-wave interaction. If you have perfect crystals, you get that kind of speckle patterns. Okay? If you have different phases, stripes, your pattern is going to be interfere. You have strange features. Okay? If you have edge dislocation, you get another different interference patterns. Okay? And because of the power of supercomputers, now you can use computer as the lens. You do phase retrieval algorithm to reconstruct the particles. So what you can do in the powdered form, if you don't focus on one particular particles, this is a high voltage spinel, goes to phase change at high voltage, okay, and come back reverse. So each dot here, okay, is a single particle that fulfill the Bragg diffraction conditions. So if you want to see ensemble behaviors, those experiments is very informative. You can do detailed analysis on each particles, and you can evaluate how homogeneous your electrode is reacting, is phase transforming, okay? But the most important thing is indeed when you focus on one crystal and you were able to do the phase retrieval algorithm and you find all these singularities within the particles. And that's where we, very excited to see those dislocations. They are static if you don't, charge the batteries, but they can move around when the batteries is being charged and discharged. And if you do the quantification of this displacement field, it's perfectly the Burgers vector A lattice parameter. So you have to do this because remember now we're looking at the 0.1% efficiency loss. So every defect, every cracks that matters. I think this is the movie to show how the dislocation moves in those nanoparticles. So I hope show you the example that the spatial and temporal responses, and I know Will does a lot of X-ray based time-resolved imaging that really cover this part with diffusion, defect, phase transformation well, right? So what's the challenge of the field is that how about in years can you design experiment that you will be able to see the lifetime degradation? And most of the people won't. I mean, if you're a PhD student, you definitely don't want to spend 10 years waiting for the cycling to finish, right? So a reliable accelerated lifetime test is needed. And also, I think a lot of industry, they might have those samples, but so there is definitely a gap here. And I think instead of doing a lot of things at a nano and Armstrong scale, because we're moving towards the thick electrode, I think those tools for doing larger scale is very much needed. We don't have a lot of good quantitative tools to look at the larger scale. Okay, so I guess for the lithium batteries, hopefully I demonstrated to you that we spend a lot of time on these 4 different categories and trying to quantify the 0.1% efficiency. So 3,000 cycles, possible if we handled all those different problems in the efficiency loss. Okay. What is beyond the lithium ion? I think every battery person have to talk about this topic, I guess. Okay, so priority research directions, I think there are different track of, of course, I think people know that we can use a single matrix to evaluate a new technology. Battery, always we have to look at the spider chart, okay? But most of the people doing solid state is hoping to make safer batteries. Conversion, I consider the lithium sulfur, lithium oxygen, all conversion type of materials. Sodium and aqueous type of batteries for low cost. And the nanostructure, I won't mention it because Professor Yi Cui's group is the, the person for nanostructure. But there's a lot of good demonstration about what nanostructure has contributed to the field. So I'm going to say a few things about solid state because I think while we are pursuing so-called a battery never catch fire, which is not true, solid state batteries still catch fire because you use metallic lithium. Okay, while we're pursuing the battery performance, we should really ask ourselves, when you have a new electrolyte, solid electrolyte, what new science can it enable? Okay, for instance, we all know silicon has a lot of problems, right, in the liquid electrolyte. You can cycle silicon very well in solid state because there's not a lot of these solvent attacking the silicon. the ethylene carbonate is intrinsically unstable with silicon. Here, my silicon has no carbon, nothing, 100% loading of silicon. Okay, so think about what new science you can do with new electrolyte, solid electrolytes. Okay, you can cycle solid-state batteries very well, but the weakest link is still the interface, because when I cycle the batteries at an elevated temperature, the degradation occur, but look at the degradation mechanisms here. They're very different from the conventional liquid electrolyte. By the way, liquid electrolyte, you can't even cycle at 85 degrees Celsius. But in solid, you can. But then because of the thermal expansion coefficient of all these layers are very different, and you're in the solid state, so the mechanical failure become one of the most important failure mechanisms in the solid state, right? So when we move to the solid state, I think a lot of mechanical engineering faculty and the students have to join us, because we won't be able to solve a lot of the chemochemical coupled phenomena. But you will see miniature solid-state batteries getting commercialized. There's no problem with that. I think the bulk, the bigger batteries with solid-state, if we don't resolve the mechanical interfacial stability issues, we still have a long way to go. Lithium oxygen, I think the science paper a couple years ago was very exciting. I had my postdoc reproducing everything Professor Claire Gray has done in the science paper. The result is absolutely reproducible. You can actually get very, very low overpotential, less than 0.2 volt. For lithium, using the combination of redox media and the electrocatalyst. You can cycle well, so my postdoc said, can I cut off at 300 cycles and you can go with better papers? But no, I would love everybody to show long-term cycling, because eventually, because of the cloggings, every cell shows degradations for the lithium oxygen. I think it's time for the battery people to really show the degradation of your cells, because we can learn a lot from the degradation. We want to learn so that we can extend this plateau as long as possible. Okay, solid state, same thing. We have full cell solid state batteries. The most interesting part is happening when something starts to drop, because then you can learn the failure mechanism and think about how you can improve the performance. Right? And I want to say for the lithium oxygen community, if you can't get the active loading up, right, 0.5 milligram, my postdoc argued with me, it's already quite outstanding. But think about the 10 times capacity compared to lithium-ion battery. But for lithium-ion batteries in my lab, I can routinely do 20 milligram per centimeter square. So even if you have 10 times more energy density per weight, because your loading is so low, it doesn't make any impact. Okay, so sulfur battery people have the same challenge. You need to increase the loading per centimeter square. Okay, this is not just doing applied research, because the transport mechanisms can be quite different when you go from thin to thick. Right? It's related to the fundamental properties of the materials. So we cannot just keep saying that we're doing fundamental research, we don't do thick electrodes. I think it's important now to think about all these things when we make them thick. What transport limit? Is it ionic? Is it electronic? Or is a combination of both? So for sodium-ion batteries, I think many of you know that Aqueon is out of business already. The upside of sodium batteries, of course, you use both electrode aluminum substrate, and sodium is more abundant. However, the energy density for sodium is lower, and I mentioned about sodium-ion batteries, because each cell has low energy density. The inactive materials you need a lot of inactive materials. So the system cost is not so clear. Sodium will be lower. Okay. We also, work on a lot of the stretchable, the flexible batteries. the known chemistry, they work quite well. You can print it, you can stretch it. Professor Zhenan Bao is an expert on stretchable and flexible electronics. I think this field will take off because the battery people will be able to power a lot of their device on the flexible substrate because now the batteries can be made flexible and stretchable. So I think I told my students I need crazy ideas. Can people come out with crazy ideas? Okay? So safety, energy, cost, power, we don't want to sacrifice everything. Anything, not everything, of course. Okay, the first question, I have one brilliant student come in, just ask the question, why only liquid and solid can be electrolyte? Why can't I use gas? Right? So really, if you have any of the crazy ideas, please talk to me, right? We want to think about, can the batteries behave like an engine? You know, when engine is heat too much, you pull it, not modern days, in the old days. You pull it aside, let the engine cool down, and you can use it again. Can I make batteries like that? The batteries self-shut down and use it again. Okay? Can dendrite form, but never short. I think that idea has been explored by some people, right? And I think the last one, can we make all the alkaline batteries cycle 3,000 cycles? I think people laugh when I say, alkaline batteries, we all throw away in the waste bin, right? Can you make 3,000 cycle? Why not? What's fundamentally preventing it, right? So I think that's where we have some good ideas. So I'm going to share with you one of the most recent work. So everybody knows that we want to look at the solvent with certain properties, hopefully in the liquid range. But we start to play with the other axis. As a material scientist, we know, pressure and temperature we can play. So based on the phase diagram, you all know the liquid is going to widen up when you increase the pressure. Okay? And then, yeah, so my crazy student, Cyrus, asked, why can't we use gas? But he increased the pressure, so the gas is actually liquefied, right? So he's been trying a lot of different gases. Okay, the outcome is very, very exciting. Because of using the gas electrolyte, the solvation shell, the solvation mechanism is very different. So we were able to make a battery that can operate at -80°C with still 60% of the original capacity. And this is just comparison of the gas electrolyte versus conventional electrolyte. So at room temperature, the performance has to be the same. Okay? But at ultra low temperature, it still works, while most of the other liquid electrolyte will freeze out. Okay? So we have actually, Cyrus is taking off to run his own startup companies. Its name is called South 8, easy to remember. UCSD is located south of 8 highway, all right? So, I think you will probably very soon see the paper in the peer-reviewed article. Again, I think this is very exciting, not because of the performance. It is exciting because it will be able to enable some new science to be done. Okay, like the solid-state electrolyte will enable a lot of the interesting new science to be done. I think this kind of gas electrolyte will enable some interesting new science to be done. Okay, and yeah, I think we were most excited is because it works both with lithium metal and lithium cobalt oxide. We know that in the lithium sulfur batteries for the ether-based electrolyte, it works well with the lithium metal, but the cathode oxidation is quite limited. So this is, again, quite exciting because you can look at the new stuff. Okay, so now jumping out of my battery field, I think for the batteries to be actually implemented, I think in Stanford you have this really huge energy institute that people think about every aspect of, energy storage, not just the materials level, right? So I think I just use one of the graph to show you in other areas like market restructuring, we have to start think about new ideas. Same here. I don't have time to talk about the open design, open energy storage system. I already told you the closed system have very limited, because thermodynamically it's a closed system, right? So if you have more Coulombic inefficiency, you have more inefficiency, you need to design open system for tolerating the inefficiency to have very long cycles. Okay, so this is not from material scientists, this is from economists. Okay, so a day ahead market means you buy the electricity 24 hours in advance. And real-time market is you bid real-time, 15 minutes. Okay? So most of the students probably don't pay your own electricity bill. I don't know. Do you know 1 kilowatt hour, how much is the bill for California? Anyway, doesn't matter. Okay? The wholesale price is much lower, only a few $100s per megawatt. So per kilowatt in California is typically 15 cents, right? So megawatt is quite expensive, but the number you see here is wholesale values. I'm talking about, for example, the entire La Jolla neighborhood. Yeah, so look at this. I mean, I don't know how many of you look at the stock market. You should, okay? This is more volatile than the stock market, okay? People at peak time, they pay 100 times more than the wholesale price in order to get the energy. Okay, why such big fluctuations? Because the demand and the supply cannot be met, right? So if in the future somebody figured out a perfect way to use batteries, to predict this without letting other people know, then they can make a lot of money. If everybody knows what's the best model to predict, then the fluctuation will go away. Right? But this is to show you there is driving force for people to do the energy storage. But I can tell you a lot of those differences due to the restriction of the energy market. You cannot monetize on it. All right? There are a lot of the energy market are not completely deregulated. So there are a lot of rules and restrictions of how you participate that don't allow you to monetize the differences. Okay? So yeah, I like this graph a lot. It says the energy storage is an underappreciated disruptor, especially for the grid. And not said by me, actually Morgan Stanley sent a report to me to read. So I think it's a very good description of the energy storage for grid, because I think for e-mobility, we have over this tipping point, but for the grid, we're still quite far away to, make a real impact in the field. So this is my students and the postdocs and the visitors and the undergraduate students. And thank the funding, I have been very fortunate to be an assistant professor at the right time. Right? It matters who is the president. So yeah, thank you very much for your attention. Yep.
For the great talk, Shirley. So the kind of the stock market price. So if anyone you're taking the batteries class next year, maybe you can think about doing that for your final project of how to predict these prices and using some algorithms. So maybe if we see that next year, we can thank Shirley for the suggestion.
A lot of money to be made.
A lot of money.
Morgan Stanley, Goldman Sachs, they're all looking at it.
So anyone have any questions about that or otherwise?
Let me just make a comment.
Oh.
You show that the performance of lithium batteries decreases with their cycle life.
Yes. Lithium ion or lithium oxide?
Lithium ion.
Okay.
Lithium ion. Can you put that figure back on the...
Lithium ion. This one.
Well, anyone that shows
The
decrease
decay.
with cycle life.
Uh-huh. Yeah, this decay is slightly, not too obvious, but a little bit.
Yeah.
Yeah.
Now, from that, can you predict how long a Prius car's going to last before it has to turn into battery?
I think that is one of the 5 priority research direction for the next 10 years. Yeah, DOE just have so right now the answer is no. I cannot predict the final life of the batteries because you can't do the simple extrapolation, right? Yeah, because sometimes the failure is sudden. But it is, when you read the report, you know, the question you asked is everybody wants to know the answer. But
the question is, what business can you make by buying old batteries that have lost their capacity because they've been used so many cycles?
Can you refurbish them?
Refurbish, yeah. Yeah, I think it's a, I don't know, $1 billion question, not $1 million, $1 billion question. Yeah, yeah. At the moment, I think I cannot predict the lifetime. Yeah. For 3 main reasons, I think we were putting the report together. I mean, one is that there are a lot of coupled behaviors, right? So Coulombic efficiency loss is coupled with maybe some secondary particle cracking, or its primary particle is, the phase changed. So we can't really know which is the reason caused those failure, those degradation. And I think the other thing is, for predicting the lifetime for rare and localized event, they don't show up in these figures. Because they are rare and localized, they don't usually show up in the Coulombic or the typical measurement we do. So,
Follow-up? But you can statistically characterize it, what fraction of the battery, there's some Poisson process, whatever. And then you can get an insurance to have it replaced. There's something of that, at least in the meantime, till you improve it.
Yeah. So actually, the economic data I showed you is very interesting because those economists ask me, Shirley, can you give me, 10 million battery data? I'm going to give you the statistical analysis. You're absolutely right. Can somebody give me all the Tesla data? We are more than happy to do those analyses. Actually, I believe there will be a lot of people trying to look for the short-term answer by having some predictabilities by the existing or the, hundreds of thousands of the electric cars that are currently running. Yeah, so I agree with you that there has to be something can be done right now for the prediction.
I remember the early electric cars, we decided to swap the batteries. So that's less of an issue then. And then some buses now use swapping batteries. So you can work around it one way or another. Yes, it's not ideal, but
yes,
you can put in the cost and whatever, get an insurance or whatever you want to do.
Yeah, I think electric cars, there will be, you will be, for swapping the batteries, I think one of the things people really worry is, for instance, that there's a reason why Apple doesn't allow you to swap the batteries, right? Sure. Yeah, I think the electric car, we'll see. I think I heard in China they are testing some of these battery swapping again. We know
they use it for buses in China.
Yeah, yeah. Mm-hmm.
Except they do it the awkward way. They have an old design where you just drive over some ramp and the new battery pushes out the old one. You don't have to stop. So it's very convenient.
I think Chris has.
Oh yeah, I have a question just about the gas or liquefied gas
Yeah.
battery. So is that, I was looking inside supercritical CO2 base?
Yes, CO2 is one of the important components. Yeah, and then small carbon and fluorine contain. So basically, we choose the lightest element possible. Carbon, fluorine, oxygen, nitrogen. You can find many combinations. Actually, there's a lot of details in the paper where you can actually choose the optimum temperature range based on the different blend of the gases. Yeah.
Surely, in a lot of oxides, especially the superconducting oxides, the electron correlation makes it really difficult to capture, theoretically, the oxygen Lincoln hole localization and so forth. In your, I think you showed one slide on the computation of it. How big of a difference do you see if you use sort of standard GGA plus U versus something like hybrid functional? Does it make a big difference on the result?
Yeah.
And is that something that we need to pay attention to? Because I think overwhelmingly now the battery community is using GGA, with some group now starting to use hybrid functionals.
I think all our calculation is based on HSE. I think hybrid function. That's definitely a valid concern, especially when you deal with cobaltate. But I think for the nickel and manganese-based oxides, the concern is less. The differences between GGA plus U, HSE, less. I think spin polarization is more important than the,
So these are done with hybrid calculations?
Yes,
Okay.
yes, yeah, and we don't have cobalt, right? So remember the real battery materials, a lot of them have cobalt, and then also a lot of, like Jean-Marie and Yang Xiaohong, they're trying ruthenium, iridium, and all those 5D, 4D stuff, the DFT definitely have problems of getting very good. So I think eventually all these hypotheses, even it's done in DFT, we still have to find ways to measure it, right? So that's why I think everybody is trying to do this in the XAS operando experiment or operando TEM. I think using liquid electrolyte is going to cause a lot of analysis problem. So that's where the other possibility using solid electrolyte, you may be able to do those measurements with much more accuracies, because these super reactive oxidative species may be more isolatable in the solid electrolyte than ethylene carbonate based.
But in terms of, you also showed the MGI, various prediction. So there, you're not doing anything remotely as fancy as GGA plus U or HSCO6. So there, then, I believe the prediction will be rather poor, right? Especially when you have things like cobalt. What do you think how do we rationalize between this very carefully conducted work that takes, months and months to calculate versus the rapid, 50,000 compound simulating voltages of oxides? Is there a disconnect, and what is your vision on that, how that can be addressed or bridged?
So I'm being video recorded, so I should be careful at, because the whole materials project is based on the hypothesis that the high throughput computation, will give us a few candidates that we can explore based on, but I think you should always look at this way. Again, the materials project that put out this data, how you use the data is based on your group's expertise. Okay, so my most important suggestion to all the students is that please don't use computation as a replacement for thinking. Right? It's not.
No
replacement.
AI for you. Huh?
Exactly. I think AI, it will happen maybe, but
No, that's better statistical models. I'm very general.
Good. Yeah, I think I'm in agreement with you. I
New
just want
statistical
to.
models are much better.
I want to be a little bit more subtle because it's a lot of investment.
I'm old enough, so I can.
Yeah. So when the data sit in front of you. So the other thing with the coherent X-ray diffraction imaging, I show you guys this singularity. This phase wrap in the phase retrieval algorithm, where you see the red is next to the blue. Yeah, I mean, literally, we were sitting in front of the data for 6 months. We didn't realize we were sitting in front of a pot of gold, right? Because if you do not know how to use the data, even the data is right sitting in front of you, you can't get the most use out of it. So statistics is the other very important thing for when we have so vast ocean of knowledge, like how do you learn useful stuff. So I think it's not contradicting that it's very good that the materials project, they can produce so many data, but I think it still takes the individual and the team's ability to use the best use the data. Yeah.
Any other questions? With that, let us thank Shirley again for a great